Microscopes commonly used to measure microobjects can distinguish objects that are about half the wavelength of the light they use. This is because the smallest dot that can be made with the light is about half the wavelength. We use this near-field scanning optical microscope, the so-called NSOM. With this NSOM, using needles smaller than the wavelength of the light can distinguish light scattered from the object in more detail. In NSOM, the smallest distinguishable size, resolution, is determined by the aperture size of the probe. Here, if you look at a structure smaller than the aperture size of the probe as shown in the picture, it is measured as a point. We measure objects with incident light at various angles to distinguish smaller than the aperture size of the probe. Although the sample is smaller than the aperture size of the probe, the intensity of light emitted from the left and right sides of the two structures is different depending on the angle of the incident light. If you create a matrix of images measured for each angle in this way, you can analyze the images through additional mathematical methods. By performing singular value decomposition of the measured matrix, SVD, we can find out the expected image when the light is composed of a linear combination of lights with different incident angles is incident. You can also see the difference in intensity between images that are expected to be different for each combination. We call this method as SVD of transmission matrix. By this method microscopic structures can be observed beyond the limitations of existing methods.